Hi, we will now discuss Ron's test for randomness. Test for randomness is an important addition to statistical theory, since almost all the classical techniques and distribution-free procedures begin with the assumption of a random sample. A run is defined as a succession of identical symbols which are followed and preceded by different symbols or by no symbols at all. The data. A typical design for this scenario involves n-numeric, binary, or categorical observations in a single column. The assumptions are: first, each observation is independent from one another. Second, each observation is from the population with the same means and variances. Hypothesis. The null hypothesis in this test is the sequence is in a random order, and the alternative hypotheses are: for two-tailed, the sequence deviates from randomness. For left-tailed tests, the sequence deviates from randomness because there are too few runs. For right-tailed tests, the sequence deviates from randomness because there are too many rounds. On computing runs, there are mainly two categories of data. The first one is binary, and the second one is numeric. Under numeric, there is computing runs based on a reference value if it's above or below, while we also have the computing runs based on up and down that is based on the previous value. In binary, in the case of binary data consisting of two distinct categories, a run is defined as a sequence where a single value is repeated one or more times. A new run occurs each time the data value changes. For this example, we have this one. We already highlighted the grouping, and the color will change when a new data or a different group is presented. So 1, 2, 3, 4, 5, 6, 7, and 8. So in this case, there are 8 rounds. For the numerical data, the first one is on reference value. For numeric data, a reference value is used to determine the runs in the dataset relative to the reference value. The reference value can be set as the mean, median, or mode of the data, or as any custom user-defined value. The reference value is used to create a binary series from the numeric data by assigning a 1 to values above the reference and a 0 to the values below the reference. In our example, let the reference value be the median, which is equal to 28.5. So in this example, this is the median of this dataset. Now, we'll mark green the values that are above 28.5, and we will mark red those values that are below the median. Thus, here is the color coding, and then we count the run as usual, similar on how we counted on the binary data. So 1, 2, 3, 4, 5, 6, 7, 8. Thus, the total run of this example is 8. Next is on runs up and down. To compute the runs up and down for n numeric data values, the sign of the difference between each value and the one previous is recorded and used to create a binary series of n-1 signs. So in this example, we count the data 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And since we have n to be equal to 10, so there are 10 numbers here, we are going to have 9 signs from these values. We compare the numbers from the previous number. So let's say we have 40 minus 44, which is negative 4. Thus, the first symbol here is negative. Then 33 minus 40, that's negative 7. So that's a negative. Then 26 minus 33, which is around negative 7. So that's a negative. And then 27 minus 26, that is positive 1. So that's positive and so on. Then we compute the runs, just like in the binary one, because we have a negative and a positive symbols here. So 1, 2, 3, 4. Thus, in this example, we have 4 total runs. Ties. When a value is exactly equal to the reference, a decision must be made whether to count it as above or below, or whether to skip the value and discard it from the analysis. Remarks. Tests of randomness are an important addition to statistical theory because the theoretical basis for almost all the classical techniques, as well as distribution-free procedures, begin with the assumption of a random sample. If the randomness of the observations is suspect, the information about the order, which is almost always available, can be used to test a hypothesis of randomness. This kind of analysis is also used in time series and quality control studies. Both too few and too many runs suggest lack of randomness. A null hypothesis of randomness would consequently be rejected if the total number of runs is either too large or too small. On the large sample approximation, for large N, the test for the number of runs R is asymptotic to the standard normal Z statistic. Z is equivalent to R minus the mean of R all over the standard deviation of R, where the mean of R is equal to 2 times n sub 1 n sub 2 all over the capital N plus 1. And the standard deviation of R is equivalent to the square root of 2 times n sub 1 n times n sub 2 times 2 times n sub 1 n sub 2 minus capital N all over capital N squared times capital N minus 1. And where n sub 1 is equal to the number of elements of one kind, n sub 2 is equal to the number of elements of the other kind, and capital N is equal to the sum of n1 and n2. With continuity correction, the z is equivalent to r minus the mean of r minus 5 all over the standard deviation of r if the value of r is greater than or equal to the mean of r. R minus the mean of R plus 0.5 all over the standard deviation of R if R is less than the mean of R. This test is less accurate than the exact test, but usually more accurate than the previously shown asymptotic z-test. Procedure. First, arrange the observations in the order of occurrence. Then, we compute the number of runs R, and we determine the critical value. If both the sample sizes of N1 and N2 are both less than 20, we can use the tables D for total runs or E for runs up and down in the appendix. B, otherwise, compute the asymptotic z-test and use the standard normal distribution table. Example 1. Passing a line of 10 persons waiting to buy a ticket at a movie theater on a Saturday afternoon. Suppose we have the arrangement of males and females in the line to be in this order. Using a level of 0.05 level of significance, Would this be considered a random arrangement by gender? Solution. The alternative hypothesis is the pattern of sequence in terms of gender waiting to buy a ticket at a movie theater is arranged in a random manner. Alternative hypothesis. The pattern of sequence in terms of gender waiting to buy a ticket at a movie theater is arranged in a non-random manner. The data consists of 6 females and 4 males. Thus, our N1 is 4, and then N2 is S is the female. And we compute, the next step is we compute the value of the runs. So 1, 2, 3, 4, 5, 6, and so on. Hence, the value of runs is equal to 9. On the critical region, since both the sample sizes, the N1 and N2, are less than 20, we use the table D and we get that the probability of R less than or equal to 2 is equal to 0.010, and the probability that R is greater than or equal to 9 is equal to 0.024, and these are the largest respective probabilities that do not exceed 0.05 divided by 2, which is equal to 0.025. Thus, we reject HO if R is less than or equal to 2 or R is greater than or equal to 9 with exact significance level of 0.034. And here below is the table coming from table D in the appendix. N sub 1 for the males is 4 and N sub 2 for the females is 6. And this will be the critical value, and this is the probability, and this is for the left tailed, and this is for the right tailed, since this test is a two-tailed test. And if you added 0.01 and 0.024, we get 0.034, which is less than 0.05, our level of significance. Since R is equal to 9, we reject the null hypothesis. Conclusion: at a 5% level of significance, we have sufficient evidence to conclude that the pattern of sequence in the terms of gender waiting to buy a ticket at a movie theater is arranged in a non-random manner. In R, we use the library desk tools, and we let X be a vector of these values, and we use the function runs test from the library test. We can put it on an exact if we want an exact test, and we can make it into false if we want um, a large approximation of it. So based on the exact test, we have 0.03333, which is almost similar to the one that we have if it's greater than or equal to 9, which is 0.034.